Good evening. Maybe it's day wherever you are, but it's evening this side. We are continuing with our thermodynamic lectures. Today we want to look at nozzles. These are simple equipment, very simple equipment, but with a lot of implications in terms of performance. So basically, nozzles is a pipe or a tube with a variable cross section, and its main function is, if we have a chamber there, when your fluid flows in there, maybe liquid or gas. In this case, normally steam is a good example because used quite extensively in steam turbines. You have it at high pressure and low velocity. When it goes through the nozzle, it will be now low pressure and high velocity. So one of the fundamental functions of a nozzle is to increase the velocity of the fluid. Now, the nozzle is able to change the speed of the fluid, is able to alter its flow, it's able to change the direction, even mass. So it can affect the fluid flow in all manner of ways, so that you can have a case where it actually releases fine mist, or you can spread it. So when you look at, for example, your garden sprinklers, all those are examples. If you look at your LPG cooker, you will see something there at the back, and looks like it's having a conduit, and that in your LPG cooking stove, you will see it there. It plays quite a significant role, and it has other main activities, which are all ranging from simple to very advanced functions. Now, we have said that when you are dealing with a nozzle, think of it as a pipe, and this pipe, its cross section varies. Cross section varies, so that what is happening is, when we have a nozzle, the flow types could be different, in the sense that, for example, if we have one which is converging, the kind of flow which will be here will be what we refer to as subsonic. The flow will be subsonic. And on a subsonic flow, the Mach for that fluid flow is less than 1. Less than 1. Mach is a unit in fluid dynamics, and it's dimensionless. And it is the ratio of the fluid flow, the boundary to the speed to the speed of sound. So the velocity of fluid to that of sound. Speed of sound. So that gives you the unit. It's Mach represents that ratio. And so for subsonic flows, which is the case where we are having this convergent nozzle, will be less than 1 in that case. Then there could be a divergent flow. Divergent. The flow here will be supersonic. So the Mach will be greater than 1. So those are the types of fluid flow which you get in this nozzle system. It can be subsonic, it can be supersonic. And as the Mach value is the ratio of that speed of that fluid, that of sound. Now, that's very important. The other important thing which you need to mention right at the onset is that when you're dealing with nozzles, it's very important to take cognizance of some of the terms. Back pressure is a very important term in nozzles. That is resistance to the flow of that fluid. Resistance to flow of fluid. The fluid flow. Then the other one is the term thought when you're dealing with an nozzle. So that if you have, for example, convergent and divergent cases, convergent, divergent case, this is the throat. The constriction there is the throat when we come to the nozzle. Very important for you to know those terms. Back pressure, very important. That's the resistance to the flow of the fluid flow and fluid dynamics. And you have the throat. Now, when we are dealing with nozzles, it's not as simple or descriptive as we are saying now. There are fundamental principles which are very important when you're dealing with nozzles. One of them is the Bernoulli principle. And the Bernoulli principle is a very straightforward principle which says that when you increase the velocity of a fluid, then there could be two possible things which will happen. There will be a decrease in the static pressure or a decrease in the potential energy of the fluid. That is, when the velocity of a fluid is increased, two things would happen, can happen. One, there can be a decrease in the static pressure. And the other one, decrease in potential energy. And so this is normally captured in that equation, captured in the equation, squared over 2 plus gz plus p over rho is equal to a constant. Where v here is the velocity, Then we have g, the gravitational, you know it all. We have z. Z is elevation from a reference point, or what we call datum level. Elevation of the system from a reference point, or what we call a datum level. Elevation from datum level. So you can think of it as a reference level. P, of course, is the pressure, and rho is the density. Now, and this marries together with the key equation which we call the continuity equation. Marries together with the continuity equation. And that continuity equation, 1 is equals to rho 2, A2, B2. Where rho, again, is density. A is the cross-sectional area of your conduit. Cross-sectional area. And V is the velocity. Now, pay attention. If the fluid is incompressible, like we are going to assume as we jump into thermodynamics, if the fluid is incompressible, then it means that its density doesn't change. for incompressible fluid, the density is constant. And if we say the density is constant for this incompressible fluid, what does that mean to that expression which you have there? What does it mean? Expression you have here? All it means is that if it's incompressible, then it means that rho 1 is equals to rho 2, that's the density. So we can say that R is A times V. And what is that? That is the volumetric flow rate. Volume flow rate. And that will be the cross-sectional area and that is the velocity, speed. So if you look at these quantities, just look two-dimension analysis. As a professional, learn to do dimension analysis so that even as you are saying volume flow rate, then you need to know whether it is what you have there is really volume flow rate, or you multiply by some factor to bring it to that, to harmonize it. So what do we have? Area, we know, let's say it's in meters squared. Of course, we are talking of the nozzle, we will be talking of millimeters squared. But just for illustration purposes, we are talking of meters squared. And what is the velocity? What's the velocity? Meter per second. So that gives you meter cubed per second. And what is meter cubed? That's volume. A second is the unit of time. So it's volumetric flow rate. When you see the word rate, it means time is there. Always remember that. Anytime you see the word rate, time, that means time is there, involved in that expression. Now, we want to assume several thermodynamic concepts. Yeah? One, the process in the nozzle is assumed to be adiabatic and is reversible. If you look at our earlier lectures, we talked about reversible adiabatic processes. There's a lecture we've talked about in that case. We have now seen a lot of circles where we're talking about the isentropic processes. Remember, we talked of Clausius inequality, where we said ds is greater or equal to dq over t. Now, we are saying that the process in the nozzle is adiabatic and is reversible. It's a reversible adiabatic process. Adiabatic. And what did we say was adiabatic? It means that heat is not transferred between the system and the surroundings. Heat is not transferred between the system and the surroundings. So if you have steam, for example, then it means heat is not transferred from steam to its surroundings. And so that this dq is 0. Therefore, dq is equals to 0. Therefore, ds is equals to 0. So that process is isentropic. That process, therefore, in the nozzle is isentropic. That's very important for us to know. That's a thermodynamic expression. So, to make our life easy and the problems tractable, solvable, we want to make several assumptions regarding the nozzle. First, we assume, just like when you wanted to make our life difficult with the pressure volume work, we assume the piston is massless, rigid, perfectly fitting, and frictionless. Of course, in reality, you know, those are quite a challenge. Those are quite a challenge to deal with. So we want to make assumptions to make our life easy in terms of understanding these nozzles. We want to assume it's a steady-state process. What does that mean? That fluid flow in the nozzle is a steady-state process. That means the rate, mass flow rate is constant and the velocity throughout all sections is constant. What is the import of that? That means there's no accumulation of energy in the system. There's no accumulation of energy in the system. So we assume the mass flow rate is constant. We assume it's constant. There's no accumulation of material and there's no accumulation of energy in the system when you do that. And the velocity is constant. That's a fundamental assumption. We have also assumed the system is adiabatic and reversible. Two, assuming the system is adiabatic and also reversible. But of course, when you go to in-depth in terms of fluid dynamics, there's the issues of stagnation or what results in some shocks in the system, but we don't want to go that way for now. So adiabatic and reversible, that means there's no heat transfer. No heat transfer between the system and the surroundings. We are assuming that the fluid behaves ideally. The fluid behaves ideally. In other words, it obeys the characteristic equation PV is equals to nRT. You can also call it equation of state. That's important for us. We are assuming that friction is minimum, if not probably zero. So we can assume frictionless. And another thing, we are assuming that the specific heat is constant. Remember, we said if you look at when in our lectures somewhere there, I encourage you to go through those lectures. We talked about Kirchhoff's equation. And there we said that there's where we used the heat capacity, which was dependent on temperature. So we are assuming in the temperature range in which you're operating, the specific heat is constant. Specific heat constant in the temperature range in which you're operating, in which we are operating. So these are fundamental assumptions which are made about the steady-state flow process in that system. And so what does that mean? What this means when we are dealing with steady-state flow process, remember we had derived an expression for fast flow in a steady-state flow processes, and we had said that dH plus dc squared over 2 plus d dz was equals to q plus or minus w. I always repeat again, plus or minus w depends on the definition of notation, whether plus is work done by the system on the surroundings, or you have chosen minus to be minus expression for w to mean work done by the system on the surroundings. So the notation is not the real issue. The real issue is use it consistently in your system. Now, this represented kinetic energy. Remember, that represented potential energy. So, if we assume, for example, this system that there's no change in the datum level, so we can assume that is 0. And we can assume that is 0. But we know in nozzles, it enhances or increases tremendously the velocity of the fluid. So, what does that mean? What does that mean? This is significant. We cannot assume it's 0. We know the system is adiabatic. We have said adiabatic and reversible. So it's adiabatic, so it's 0. And of course, no, there's no work in our system there. So what does that mean? That means that dH plus dc squared over 2 is equals to 0. So if we just rearrange these quantities, we have minus dc squared over 2 is equals to 0. So integrating this within some limit which you can pick, let's say from 1 to 2, we have integral minus dc squared over 2 from 1 to 2. And of course, very simple, just using our traditional identity which you have always used, the integral of dx is simply x plus c. And of course, it's the integral constant. If you put the limits, then you don't have to worry about that. So that's what we are going to use there. And of course, we know what else is that identity. I always like reminding ourselves that you don't take things for granted. plus 1 plus C. We have that identity, so we are going to apply it that particular system there. So let's see what we get. Let's see what we get now. So we have H2 minus H1. H2 minus H1 is equals to minus the integral, that is C squared. We have this as C squared over 2, so that will be, remember, we'll have this particular case, if we integrate this quantity, that is for C squared, if we integrate it, we will have C squared over 2, 1, so that becomes C2 squared equals minus over 2 minus C1 squared over 2. And so what do we have here? If we factorize, we take the LCM, we have C2 squared minus C1 squared over 2, it's H2 minus H1. So if we cross multiply, we have 2 into H2 minus H1 is equals to C2 squared minus C1 squared. But you know, the nozzle is enhancement of the velocity. So we can assume, without too much error, that C1, C2 is much, much greater than C1. So that we have then 2, H2 minus H1 is equals to C2 squared, or C2 is basically the root of 2, square root of 2 H1. Those are assumptions you have taken, put in place. And this particular assumption, which you have worked with using that steady state expression for first law of thermodynamics, is fundamental, because it's the law of conservation of energy, which basically tells you that you cannot create or destroy energy. It just changes forms. It just changes forms. And that's very, very important in helping you determine the thermal efficiency in this particular system, and also efficiency in the energy dynamics of a system, especially if, for example, you're dealing with a steam turbine. And if you look at our lectures on steam turbine, I talked about the peloton. And so we have the double casing. That's trying to draw it to reasonable accuracy. Reasonable accuracy. We have the duct there. Let's say we have here our nozzle. It will do better than that. Let me push it a little bit down. Not drawn accurately. It's not drawn accurately. But you get the gist of the representation. So we have our runner here. And we have our blades. So we are saying you have a nozzle here. So whatever steam is coming through the duct, we have this is our casing. We have our casing there. So, like you have said, you can get a fine mist or you can get a spray jet. And in turbines, mostly we have spray jets at very high velocity. So that jet there is that spray jet. So you can imagine parks that and rotates, and of course you can do reciprocating work with that particular turbine. You can connect it for generation of electricity. We have discussed that when we talked about steam turbines, their types, and how the process works, including their PV diagrams and so forth. So I encourage you to look through those so that it helps you marry these facts together, so that you get a better understanding of the things. So I think we'll stop at that point. So let's meet next time.